Ladies and gentlemen, welcome back. So here we go with the first video from Chapter 8. And Chapter 8 is about potential energy and conservation of energy. But I think that if you want to boil this down, this one idea of conservation of energy is really what this chapter is about, and it is so fundamental to physics. It becomes something that really makes our lives easier when we're trying to solve certain problems. If you think back to kinematics and all the equations of motion and acceleration, some of those problems became a bit challenging to start to solve until we saw how we could utilize Newton's laws of motion, particularly the second law, F equals ma, and the third law, action and reaction. And a few of those problems became easier to understand, easier to deal with. Well, we're going to see a similar thing happen here. When we are looking at a problem and looking at it in terms of the energy and the changes taking place in the energy, then the approach and the solution to a particular situation might be significantly easier than it would be if we were using Newton's laws. Conservation of energy. You've heard this before. Basically, energy cannot be created or destroyed. It must only be transformed. You can change the form of the energy. You can move the energy from one place to another. So if you have a person running on a treadmill, then the treadmill actually might be a passive system. The person is using some chemical energy stored in their body, glycogen, fat reserves, all those things, and they're creating some kinetic energy from that chemical energy. And the kinetic energy that they're using is getting turned into some mechanical energy here, so they're actually running along and moving the belt underneath them. So in the sense, the source of power is the person, not a motor inside. But you know what's going to happen. Somewhere in here, there's going to be a bad bearing and there's going to be some friction. Now, what the friction is going to end up doing is taking some of that kinetic energy and converting it into heat energy, or thermal energy if you like. And so we're seeing energy change forms, and some of the energy would be leaving the system possibly, and some of the energy would be staying as that mechanical or that kinetic energy. But we're going to see this over and over. We're going to see electrical energy converted into kinetic energy, which might be converted into something else. So conservation, now there are other conservation laws, not too many of them, but they're really, really important for us. Now, as we're going to do this, we have to look at forces and how these forces are going to affect the energy and the type of energy that we're dealing with. So forces are generally broken down into two categories. You've got what are called conservative forces and non-conservative forces. Oops, conservative. Get rid of that. So, what's the difference here? Well, essentially, a conservative force, if we look at this, then there's a couple definitions provided to us. A conservative force will do zero total work on any closed path. That's one way to look at what a conservative force is. Well, okay, the idea of a closed path, what this means is that if there's a starting point, then whatever happens, there might be some place, some travel. Okay, but if the path is closed, it was going this way, then across, back this way, eventually headed down, and back this way, and across again, and back up, back to the starting point, that's a closed path. And it turns out that for conservative forces, If the path is closed, if it ends up back where it started, then the total work done would be 0. So in that sense, on a closed path, if there's 0 total work done, then there's 0 change in the energy. So things are conserved. All right. No issue there. Another definition for conservative forces, another way to look at this idea is that I'll put this here again. For conservative forces, the work that is done is independent of the path, of the pathway taken. So we've seen this before in the previous chapter. We noted that if you're going to use a ramp to get an object to a greater height, okay, that's cool. It makes a lot of sense because using the ramp to get this object up to this new height means we get to use a smaller force. Well, the trade-off is we are pushing with that smaller force across a longer distance. So if we take this path up the length of the ramp, essentially up the hypotenuse of that right triangle, then we're doing a certain amount of work. If instead we were to lift this object up this height to that same vertical position, okay, turns out, well, we have to use a greater force, but we're covering a shorter distance here, and we end up doing the same amount of work. So we see that the work done here is equal to the work done here. The work is independent of the pathway taken. That's what we mean. It doesn't matter what pathway you take. You could have a starting location here at location A. You could have an ending location B. And maybe you take pathway number 1. Or you take pathway number 2. Really wouldn't matter. The amount of work done between pathway 1 and pathway 2 would be the same, as long as this is a conservative force that we're talking about. So we'll come back to that. With non-conservative forces, just the opposite would be true. So if you're trying to push a box across a floor, all right, well, imagine that this is a floor plan of a room. We're looking down from above. We have a box here, and we're going to try to get the box to this location. So here's location A where we start, location B where we want to end up with the box. If we push the box straight here, we have to overcome some friction between the box and the floor. And it's easy to see that, well, the work done across this distance by friction is going to be a different amount than the work done across this total distance here to here to here. We would have to add up a distance there, a distance there, and a distance there. We're still overcoming the same amount of friction, but because of the larger distance we're traveling, the work done by the friction would be much different. And so the friction itself would be considered a non-conservative force because it does matter what pathway you take. If it doesn't matter what pathway you take, it's going to be a conservative force. If it does matter which pathway you take, you have a non-conservative force. And friction is a classic example, the famous example for non-conservative forces. Okay. So next, let's take a look at an example. Let's get more specific here. And in this example, we're going to view things two different ways. We're going to look at getting a box from a location here at location A to a location here at location B. And let's say we're viewing this from the side. So here's our floor level. And let's look at two different pathways for getting the box to location B. So, okay, just a little box, no big deal. Let's say we're going to do this So we're moving the box horizontally, we're moving the box vertically, we're going to move the box horizontally back here, and we're going to move the box down to location B. This is going to be one of our pathways. Another one of our pathways will be moving the box vertically here, and then moving the box horizontally there. And so either pathway we take, let's call this pathway number 1, pathway number 2. Either pathway gets us to location B. Awesome. Well, we have some distances here. That is going to be a vertical distance of 1 meter. This will be a horizontal distance of 3 meters. Along pathway 2, we have a horizontal distance, let's give this one 6 meters. And vertically, we're going to lift 2 meters up. Horizontally here, we will travel a distance of 3 meters. Vertically downward right here, this will simply be 1 meter. Okay. So now what's happening in terms of the work done on each of these pathways? We're going to focus on the work done by gravity. Let's see what gravity is doing across or along each of these pathways. So what we want to make a note of is, well, the fact that gravity is only acting straight down, and here our pathway is up. So for this first segment, we have the work done by gravity. Well, this is going to be equal to FD cosine theta. And theta is the angle between the force and the distance. So theta is 180, just gives us a negative value here. The force is going to be the weight of this object. So if we're going to find the weight, well, we need a mass, don't we? So let's give this object a mass. It's just nice, even 4.5 kilograms. So the force will be equal to the weight. The weight is going to be mg. We have to multiply by the distance. So we've already taken care of cosine theta. That's in our negative sign here. So we have our mass of 4.5 kilograms. G is going to be our 9.81 meters per second squared. Distance traveled here, 1 meter. Handy dandy calculator. Round numbers, 44.1 joules of work. Actually, really what I ought to do is take a look at sig figs. I got 2 sig figs, well, really 1, I guess. Let's call that 1.0. Let's give us 2 sig figs here. 44 joules of work done by gravity, just in the first segment here. And how about this second segment right here? Well, what's the work done here? The distance traveled, this is, this part of this work done by gravity is just that first segment. We're actually going to have to add the work done by the second segment, aren't we? So now, pathway 1, by the way. Sorry about that. Well, we have a distance of 3 meters, so we're going to have force times distance, and again, we're going to want to do cosine theta. But look what's going on. If the weight is pulling down, but our distance is to the right, the angle between those two is 90 degrees. With the cosine of 90 is 0. So regardless of the force and the distance, doesn't matter how far this segment is, doesn't matter how long that is. We're multiplying by 0, so this simply becomes 0. And we have the amount of work done by gravity. Oops, that's supposed to be joules. Sorry about that. That whole thing goes to 0. Okay, so along pathway number 1, gravity is doing 44 joules of work. What about pathway number 2? Well, across pathway number 2, we have a 6 meter segment, a 2 meter segment, a 3 meter segment, a 1 meter segment. But right away, I can see that for this 6 meter segment and for this 3 meter segment, the work done by gravity is going to be 0, because these distances are perpendicular, or 90 degrees, there and there. They're 90 degrees away from the force from the downward weight. So I really don't have to do any math, do any calculation for those two segments at all. I do need to look at the upward segment here, the work done there, and I need to look at this downward segment here. Okay, so this is going to be for pathway number 2, work done by gravity. I know that I'm going to need a force times the distance times the cosine of theta for the upward pathway, and I'll need to add a force distance cosine theta for the downward pathway. Okay. So here's the deal. The force is mg, and it's pulling straight down, but the distance is upward, so the angle between them is going to be 180. mg, and cosine of 180 is just -1. So here again I have my minus sign. So mg is my force.
Nicholas Galindo, please report to the reception
Sorry about that announcement.
Nicholas Galindo, please report to the reception desk.
mg is the force. The negative sign comes from cosine of 180 and times my distance. Okay, and I'm going to add to this the work done by gravity in this downward segment. So in this case, the distance traveled is down, gravity is pulling down, the angle between them is 0, cosine of 0 is just 1. So I don't have a minus sign here. The force is mg, and I have the distance. I have to pay attention that this distance and this distance are not the same value. So if you want some sort of marker for that, you know, segment 1, segment 2 kind of thing, that's fine. So what is the total here? Okay, so I've got mass of 4.5, g is 9.81, and distance 1 here, let's call that the the upward 2 meters. And here, mass of 4.5, g 9.81, and this distance here, the second vertical distance, that's just 1 meter. Okay, so when you crunch these numbers, it turns out you are still going to get negative 44 joules as the work done by gravity. It turns out that it really is independent of the pathway that we take. And that's kind of nice. So gravity is definitely shown to be a conservative force. It doesn't matter what pathway we take. If we talk about going from one place to another with or against gravity, then the work done by gravity is the same for all pathways. And that's pretty nice. There's another way to look at this situation, though. And so now, to begin this example, I was looking at it from the side. And so here's our ground, and we were moving horizontally, moving up, moving horizontally, moving down. And here we're moving vertically up and then moving horizontally to get from A to B. Well, what if, instead of looking at it from the side, what if we take a different viewpoint and again, look at it from above, look at it from a top view. And instead of carrying this and lifting it, let's say we're going to have this, this floor space, this floor plan. And so I'm going to identify locations A and B once again. But now I'm going to slide this box across the floor. And so I'm going to slide across the same 6 meters. It's kind of, my B is going to be off center here, off location. That's okay. I'm going to slide vertically. I'm going to slide back. You know what? To be honest, I'm not happy with that. Let's do that better. Let's have it do better. Here we go. Top view. Okay. So looking at a floor plan, I'm going to start at location A, and I want to end up at location B. So I have two pathways I'm going to take, and this will look very much like the first illustration that we used. But in this case, I'm sliding the box across the floor 6 meters this way. I'm going to slide it across the floor here. 2 meters this way. I'm going to slide it across the floor here. 3 meters, and I'm going to slide across the floor here 1 meter. And that's one of the pathways I could take. The other pathway I could take is going to be sliding across the floor 1 meter there, and then 3 meters there. So I've got, again, pathway number 1 and pathway number 2 that I can compare. And in this case, what I want to look at is not the work done by gravity, because there will be no work done by gravity. Gravity is in this illustration sort of pushing down into the page. And so all of these distances are perpendicular to gravity's direction. And so cosine of 90 is 0, and then you get no work done by that force. But there is a force doing some work here. As I push, friction is opposing that push. So how much work is going to be done by friction across these two pathways? Let's look at pathway number 1. And instead of looking at gravity again, we're going to see work done by friction. What's happening here? This will be kinetic friction. Okay. So I have 2 segments here. I have a 1 meter segment, and I have a 3 meter segment. This is pathway number 1. And so how do I set this up? Well, friction, a little off to the side here. Work done by friction. Well, I need a force of friction, and force of friction is mu kinetic times normal force. But so here's the force of friction I'm dealing with. I'm going to also have a distance, and I'm going to have a cosine theta. There's my force, my distance, and my cosine theta. And I have to do this for each segment of the pathway. So here in pathway 1 there are 2 segments, so I have to do this twice. So I have to look at this coefficient of friction. I'm going to need that value. Let's give it some decent level of value here, some decent friction, and say coefficient of friction of 0.65. Nice. How much work is done by this? So I need to set this up. It turns out that if I'm pushing in this direction, then friction is opposing that motion. So the angle between the force of friction and the direction of travel is 180. So I'm going to have a minus sign here. Cosine of 180 is -1. And so I have my coefficient, my normal force. Well, the normal force pushing down into the page, pushing up, holding our box up, caused by the floor, is going to be equal to mg. There's our force. There's our normal force, I should say. And combined, these make up the amount of friction that we're experiencing and our distance traveled. And then I've already taken care of the cosine of 180 with that minus sign. But now, I'm going to add the work done by friction for the next segment. But again, the distance traveled is to the right, friction is acting to the left, the angle between them is 180. And so the cosine of 180 is -1, so I need a minus sign here. And I'm going to add the negative of that amount of work done. Or I should say it has a negative value. So again, I have the same coefficient of friction. I have the same normal force, which is mg. And I have the distance traveled, so there's 1, and here's distance 2, if you like. And so now I have to find the total here. So 0.65. M is still the same mass. So from that previous problem, the mass was 4.5 kilograms. G is 9.81. The distance for segment 1 was just 1 meter. Easy peasy. Now, I'm adding the opposite of this value here. 0.65. Mass of 4.5. G is 9.81. Distance of the second segment of this pathway was 3 meters. Okay, but remember, everything is negative for that part, for that segment of this pathway. Number crunching time. Okay. So what I get is I'm going to do this in two parts to keep my own sanity at the moment. I have a negative 28.7, and for here, $86.1, and the total across this first pathway $114.8, and really for sig figs, I'm looking at 3 sig figs, 115 joules of work across pathway number 1. That was page 5, sorry. Got to add that. So now I need to compare the amount of work done by friction across pathway number 1, which I've just found, to the work done by friction across pathway number 2. And it turns out I can clearly see right away there's not going to be any segment of this pathway where the work done by friction is 0. And in fact, look at this. Really what I can do if I want is I can say, well, there's 6 meters, there's 2 meters, there's 3, and there's 1. 6 and 8 and 11 and 12 meters of distance traveled. So wouldn't it pretty much be the same result if I looked at the total distance traveled? Because look what's happening. It doesn't. The distance and direction doesn't really change the amount of friction force. The amount of friction force is coefficient times mass times g, and then I'm simply multiplying by whatever the distance is. And here I'm adding the distance, and that's the same component in each one. Here's what I mean. Here's what I'm getting at. Page 6. So for friction on pathway 2, the work done by kinetic friction. Well, I know that there are these 1, 2, 3, 4 different segments along this pathway. Each of those segments has a given distance. And so I'm kind of saying to myself, well, all right, look, I know that the work done is going to be a negative value because along each segment, no matter which direction we're traveling, friction is going to oppose that direction. So if we're traveling this way, friction is that way. If we're traveling to the left, friction is to the right. If we're traveling down, friction is up. So the angle is always 180, and cosine of 180, we're always getting that -1 value. So I can look at this and say, okay, I'm going to say, what is the force of friction times the total distance?